you're going to be looking at the head of your data frame. So instead, try doing df.head, and then you should be able to see the top 5 rows of your data frame you loaded in. Yeah, I hope that fixes it. Okay, so I think I'm going to move on now, but yeah, if I'm moving too fast and you don't get a chance to copy down code, just put a message in your team chat or at me, and I'll try to slow down. Okay, so next thing we're going to do is something, again, familiar, which is training and splitting our data into training and testing sets. And this is something that's crucial in basically every machine learning project you should be doing, right? Because you won't know if you've overfit or underfit your model if you don't have an evaluation testing set. So we're going to import the train test split function from sklearn or scikit-learn.model_selection. And then once we have that import done, we can say xtrain. Oh, what comes before the scatter plot? We've just imported the library so that we can we've just imported the library so that we can scatter it. So we're saying import matplotlib.pyplot splt. Is that what you meant, or did you mean the cell above? The cell above. This is just looking at the x and y, and then above that we had defined the x and y values. So we had said x is the years of experience and y is the salaries. And then after that, we were just experimenting to see what x and y were looking like. So that was x and that was y. Does that answer your question, Jad? Okay, cool. So yeah, we're just gonna say x train, comma x test, comma y train, comma y test, and you need to have the variable names be in this order, and that's because the tuple that train test split function returns is actually in this format. So the first value will be the x train, second value will be the x test, third value will be y train, and fourth value will be y test. And then we're going to use the train test split function with xy, and then the test size is equal to 0.15. And that's going to mean basically 15% of the data. Yeah, Caitlin. Where do you want me to go? Is this good, or do you want me to go up to the definition? Higher, okay. I'm going to delete this cell because this is not important, and then hopefully and if I can clear the output on this cell for now. Okay, now hopefully people who are here can see this, and then people up here can see this as well. Okay, is that good? Okay, cool. Thanks, Johnny. Yeah, Johnny, if you can keep doing that for people who need to catch up, that'd be great. Okay, so once we have the train test split with our 4 variables, now we have a training set with x train and y train, and a testing set with x test and y test. If you guys recall from last time, we actually had to convert them to numpy arrays. And what this dot reshape -1, 1 is doing is just adding an additional dimension to the x train. And okay, sorry, 1 second. I see a question from Kexon. That's not the code for the graph yet, Kexon. Can I see the code for the graph? Okay. Yeah, and when he sends that, I'll go over that. But for now, we're just converting them all to numpy arrays. And this part right here is adding an extra dimension. So if you think about it like lists, let's say you had a list of 1, 2, 3, 4. All this does is it puts an additional set of square brackets around. So now it's the exact same values being stored. It's just a 2-dimensional array. And the linear regression model that scikit-learn or sklearn has expects it's compatible for both multivariable and single variable ones. But to be compatible for multivariable ones, it has to have the functionality to take in multiple lists. So when you're passing in just one, you need to add an extra dimension so it can be interpreted as 2 dimensions. So you're just going to go ahead and convert them to numpy arrays and then add a dimension for each of the variables. Yeah, the function Kexon is just plt.scatter, and then you're going to just input xy, not a core scatter. Yeah. Okay. So I'm going to leave this up for people who are still catching up, but I'm going to move on to the next block for now. And then, okay, actually this block is just looking at what are the shapes of the block. So now you can see, now you can see that we have these, I didn't run this cell, yeah. Actually, I haven't ran a lot of these cells. Let me rerun the graph, rerun the splitting, rerun this, rerun this. Okay, so now you can see that each of the things have an extra dimension. So previously they were just 25, 25, 5, and 5, but by adding the dimension, we have a 25 by 1, 25 by 1, 5 by 1, and 5 by 1. Okay, so now that we've looked at our shapes and we've converted them to NumPy arrays, we can start our training process. So we're going to import this nice model from linear regression, which is from sklearn.linear model, import linear regression, and then we're going to create an instance of this import. So we're going to say model equals linear regression, and we're going to fit or train this model to the training data. And that's all this code is doing here. So I'll give you a second to go ahead and train your model. So yeah, now you should have hopefully trained your model. And then if you have, I think I'm seeing an issue in here from Robert. Yeah, okay, thanks, John. Okay, so the next block is we're going to make some predictions with the model we just made. So we're going to say preds equals model.predict x test. And then we need to do this so that we can evaluate. So we're basically having our model predict on the testing values that we set aside from the start. And then we're going to see how do the predictions that the model made compare to the actual truth values that we've stored in the y-test variable. So to do that, we're going to use something called root mean squared error. So what is this? So the mean squared error is, well, I guess to start, the error is basically the difference between the prediction value or number and the real number. So if, let's say, the predicted salary was 40,000 and the actual salary was 50,000, the error would be 10,000. But you know how the prediction could be either over or under the real value. So you have a potential of getting a negative error. And that makes it a bit harder to interpret. So what we do is we do a mean squared error to get rid of all those negatives. And then we're up to these squared massive values. But to actually understand how far are we in our predictions, what we have to do is go ahead and square root that. And there's quite a few ways you can square root the number. I mean, this is just one of them. We're doing np.square root, which is a NumPy square root function. And that is the root, RMSE is root mean squared error. And that's going to tell us the average value, average amount we were off. So if we run this, and let's say we look at our, I don't know if I have it here. Yeah, let's take a look at our RMSE. So RMSE is 6,657. Now that sounds like a massive number, but it's actually pretty good in terms of the amount of data we had and the context that we're looking at, right? These salaries are 100, let's say they're 100,000. Our model was able to predict, in the range of 94,000 and 106,000, which is fairly impressive, right? Just looking at the years of experience, the model was able to look at this data, train on the data, and then do this. Okay, so that's good. We're going to get into some, I guess, let me give me a sec to explain this, but we're going to get into some data analysis and kind of looking at what are the results we have and how can we use a real world application of this, right? So the first thing we're going to do is we're going to add two more columns in our data frame. So the first one's going to be predictions. So predictions is model.predict np.array data frame user experience.reshape this. So we've actually done all this before, right? If you guys recall, this is really just x, and this is just reshaping x as a 2D array, and then this is just converting it to a NumPy array, right? So we've actually done all these steps. So why are we doing it all again instead of just putting in, and why are we predicting on it after all that? Because that's all we've done so far. Why don't we just say data frame predictions equals preds, right? We already have that variable. Well, the reason is we have actually sorted some of these values as we've gone through this training process. And that same does not apply for the newly made predictions. So what we're going to have to do is kind of redo that in one line and have that be stored in the predictions. The numbers will be the same because what our actual linear regression model has done, it has now calculated some m value and some b value in the mx plus b function. So if you just do it all over again, you're going to get the same result. And then we have a new row called score. And this is basically scoring the salary. So we say data frame salary minus predictions. So if, let's say, you have a high real salary, but the model said for that many years of experience, you should only have this much money, your score will be positive, meaning that it's a generally good deal. Right? It's a generally good pay for the years of experience that you have. But let's say the predicted salary for the amount of years of experience you have is higher, and the actual salary they're offering is lower. That means that your it's not a very good pay for the amount of experience you have. So we're going to create those new rows, and let's take a look at what our data frame looks like now, just by passing in df. So maybe I'll just do df.head so it doesn't take up my whole thing. Okay. So you can see now we have the years of experience and salary like we did before, but now we have two added things. So we have the prediction and the score. So we can see here, I mean, this is fairly impressive just looking at this, right? We have the salary of $39,343, and our model was able to predict $36,000 salary for this. And our model was able to predict a 43. Well, the real was a 43,000. The model was able to predict a 45,000. And you can see it's generally fairly good. And you can see these score values. So these negative values are generally worse offerings of a salary, because it basically means that the salary that they have up is not well paid for the years of experience you have. So we can see that these ones are maybe some better deals, like this 7,429 score versus this negative one. But to actually get an idea of what is the best, what we're going to do is we're going to sort our data frame using the score value. And what that's going to do, and you can just copy this code, data frame equals data frame.sort value. So we're going to sort the values with the score column having the ascending being false, right? We're going to ascend. And then you can see if you look at we're going to descend from the top, the best values at the top of the data frame and the worst values at the bottom of the data frame. Now, if we look at our data frame now, we can see like the best job offering had a score, had a $10,000 higher salary than what they should have for the years of experience, right? This guy at 19 years of experience is being offered $93,000, whereas let's say this guy with 25 years of experience is being offered $100,000. Even with 6 years more of experience, he's only getting a marginal amount more money, and that's what our model has done here. Okay, and I'm just going to collapse this for now because I know people want to catch up. So I can have some of the upper code still up there. Let me take a quick look at the chat to see if anyone was having some trouble. Okay, looks like Johnny got it there. And yeah, Johnny got it there as well. Okay, thanks, Johnny. Okay, so now what we're going to do is we're going to say the best or the top or the best paying jobs. We're going to say top equals dataframe.head3. And what this will do is if we actually take a look at top, right? It's going to store the best 3 out of the data frame we just looked at, the best 3 deals or best 3 pays. And then we're going to have a bottom, which is dataframe.tail3. And what that's going to do is it's going to give us the bottom 3 worst deals with low scores. And now that we have these best deals and worst deals, we're going to make this cool graph where we can see, color coordinated the quality of deals. So we're going to basically plot plt.plot the years of experience versus the predictions with the color K. And color K is really color black. It's just that B is used by blue. And this is basically just plotting the line of best fit, right? It's taking those input values and then it's putting the value that our model predicted. And then that's going to be the line of best fit that our model found. And then in blue, we're going to plot just, the regular years of experience and the real salaries. And that's just the scatter plot that we saw earlier. If you guys remember, we had made the graph up top. It's going to replot those points as well. And then we're going to have the best ones put in green. So we're going to scatter plot the top years of experience and the top salaries, and the bottom years of experience and bottom salaries. So the top ones are going to be color coded in green, and the worst ones are going to be color coded in red. So this may take a minute to type up. Just once you're done, this is what it will look like. So you guys are going to see that you have this graph where you have all of these points in blue. And these are the same points we looked at earlier, with the years of experience here. And we can add some labels here. So we can say plt.x label, years of experience, plt.y label, salary, and we can run it again. So we have the years of experience here, right? And then we have the salaries here. And you can see in the blue, we have all of the different, years of experience salary points. We have the black line of best fit, which our linear regression model found. So it looked at this data and it found this line. And then in the red, we have the worst scoring jobs. So which ones were the worst, I guess, deal in terms of how many, or the worst salary for the years of experience someone has. And then in the green, you see the best 3 paying jobs. I'll give everyone a minute for that. And then after that's done, if anyone wants me to go back and explain or go back to some code that you missed, I'll leave a couple minutes for that before we move on to multivariable linear regression. And if you're done, just go ahead and put like done in your team chat so I can get a grasp of where everyone is. Okay, cool. So we have 1 done. Yeah, and then either put done or put go up, and then you can just tell me when to stop, and I can help you out there. Okay, I'll give everyone I'll allocate like 2 more minutes for this. We'll give until 6:40 for people to either say done or say, hey, go back up and show me this part or show me a certain part that I missed. Yeah. Yeah, besides that block looks fine. If some other error persists after, I don't know why the marker is at the start of bottom, but yeah, there is a period after your bottom.salary. Can you scroll up after the bottom equals df.tail3 code? That's this right here. So scroll up after, like here. See if I can like zoom out or something. Okay. And maybe I can clear the outputs here. Okay. And if anyone wants me to scroll up more, Patrick, is that good, or do you want a little bit more up? Yeah, that's good. Okay. Yeah, I hope you guys can still see it. I know it's kind of small, but okay. If anyone is not caught up, take a screenshot right now because I'm gonna get started with the next part. I'll give about, I guess, a few seconds for that, and we'll move on. Okay. So Now we're going to be looking at multivariable linear regression, and this should move fairly quickly because a lot of the processes are actually really similar. It's just conceptually it's quite different. So we're going to start by setting a new path, and what you guys can do is click add data and then search KC house data. It's by Shiva Chandel. And then same way, just go ahead and add the data set. I've already loaded it in on this notebook, but just go ahead and do that. And once you do that, once again, go on the drop down, go to the far right of the CSV file, click the copy file path, and then paste that into a path string. If you guys want to have both, like you can run either at a certain time, you can use different variable names. I'm just overriding the old variable names. So path is no longer storing the old path. It's going to be storing the house data CSV path now. But you can always rerun it later. Okay. So once you have your path string storing the path to your CSV file, we're going to go ahead and load in the data again like we always do. So we're going to say data frame equals pd.readCSV path. Again, you're going to have to make new variables if you don't want it to overwrite, but I'm just overriding the last data frame because we're not going to be working with that project anymore. So I'm going to run that, and now data frame is going to hold the values from my path. So I'm saying data frame equals pandas.readCSV function and passing in the path. And then I'm going to take a look at kind of what is the head of my new data frame. So here we have a bunch of attributes of a home. So we have the ID, which is not really relevant to us. We have the date, which is not relevant to us. But then we have the price, which is going to be our independent or our dependent variable, what we're predicting. And then we have like a bunch of different dependent variable factors. We have the number of bedrooms the home has, the number of bathrooms the home has, the square foot of the living room, the square foot of the full lot, the number of floors the home has. Does it have a waterfront? So 0 would be no and 1 would be yes. The view, I guess, a rating, and then there's a grade. There's the square foot above, the square foot of the basement, the year it was built, the year it was last renovated, the zip code, the latitude, the longitude, and then there's some extra values here. I'm not quite sure what those mean. But what we're going to do here is something that we all have to do is set the dependent variable to the price, right? Because we want to predict the price of the home given all these factors. Now, here's where I'm going to give you guys some freedom, and we can kind of see who was able to get the highest results with the dependent variables they chose. So I've done a super simplified one, which is just the bedrooms, number of bedrooms, number of bathrooms, the square foot of the lot, and the number of floors there are in the home. And then I want you guys to just, choose whatever variables you think could yield higher results. If you think that's just the square foot of the lot, then go ahead. If you think that's, or actually, I want you guys to choose at least two, because we want to try the multivariable portion of this. So if you think that's just the square foot of the lot and the number of floors it is, so be it. If you think every single one of these should be used, do that. But how you're going to do it is say x equals data frame, and then you have to pass in, instead of passing in, just the different rows, you have to pass in the different rows as a list to the data frame as a key. So you say data frame, and then in square brackets, you put a list of all of them. So there's kind of double square brackets on either side. And then once you've done that, I'll give everyone like a minute. I'll give everyone to like 6:45 to choose whichever variables you like. And yeah, Caitlin, actually, you can add whichever ones you like in yours. We're all going to try different ones for x. So like for me, I've said x equals, and I've passed in the list of these four. So then in yours, just put whichever ones you like. And then at the end, I want you guys to print. We'll print like the different, like the how far off we were, the root mean squared error, and we'll say what factors did we use, and we can see which ones yielded the best results. It's like a collective effort. Okay. I guess I'll give like 15 more seconds if anyone's still. I guess if anyone's doing all of them, they're still typing everything. But yeah, I'll give a couple more seconds for that, and then we'll move on. Okay. So what we're gonna do now is we can just take a look at what or I guess everyone else will be different, but you can take a look at what your X looks like. So for me, I've got this. I'll just look at the head for now, but I've got my bedrooms, bathrooms, square foot, and lot floors. And then if I look at my y dot head, I just have the corresponding price of each of these homes. Okay, I don't know what the supply code is, but yeah. Okay, I'm gonna delete these just because I know people might be wanting to catch up, but you can leave yours there. Um, so I just want to have more space for code to be up there. Okay. So then again, we're going to be splitting our data into a training and testing set. So last time we went with 15%, it was a smaller data set. This time I think we can be generous and give it 20%, but feel free to experiment with a different number if you'd like. So we're going to say x train, x test, y train, y test equals train test split. And then we're going to pass in, the x, the y, along with the testing size. And once you run that, it'll split your data up. I'll give a minute for everyone to type that. And then, yeah, if you guys recall, the import is from sklearn.model selection import train test split. Actually, yeah, I mean, we can leave it up there, but technically we did import it like on the last one, so we don't really need it, I guess. But I guess if you want to run them separately, it's good to have it. Okay, I guess that'll apply in a bit too. But okay, so next we're gonna go ahead and convert them to numpy arrays. And if you notice, this time we don't have the dot reshape. Like last time we had a dot reshape and then we had a -1 and a 1. And the reason we had this last time was it was a single variable linear regression, right? So it was actually only one dimension there. But in this case, we actually don't have to do that reshaping in the x values because they're already in 2 dimensions because we already have so many factors we're considering. So we can just convert them to regular numpy arrays, and by default, the x values are going to be 2-dimensional. So we can do that. And I'll give you guys a minute to type this up because I know this is kind of a monstrosity. But once you have that, it'll convert your training and testing values all to numpy arrays to be passed into our model. And then the next thing we're going to do is literally train our model.